One of the important parameters to consider while you're choosing an IC logic family is fan-out. Fan-out of a logic gate gives an idea about how many inputs can the output of the logic gate drive. So for example, if I assume that the fan-out of an AND gate is 3, then it can essentially drive 3 more gates. So for example, if this is my AND gate and I said that the fan out of this AND gate is 3, that means it is capable of driving 3 more gates. If you add in another gate, it can be any gate. So if you add in another gate, then there is going to be a loss of data. We do not know in which gate will there be a loss of data. It can be the first OR gate, it can be the third OR gate, or it can be the inverter or the second OR gate. But you cannot reliably drive 4 more gates. Therefore, the higher the fan out, the better. So you want to choose a logic family which gives you a higher fan out. Now, what if the output of the AND gate, you want to drive, let's say, 10 logic gates, and the fan out of the AND gate is 3? How do you overcome that problem? So there should be some way where you can boost the signal. And to do that, we use something known as a buffer. A buffer or a buffer gate is nothing but if you have an input and an output. So if you give a 0, the output of the buffer is going to be 0. If you give a 1, the output of the buffer is going to be a 1. So what a buffer does is it's going to boost the levels. The logic remains the same. That is, you give a 0, you get a 0. You give a 1, you get a 1. But it boosts some of the other parameters like maybe voltage or current. And using that, you can drive more number of gates. Typically, with buffers, you can have a fan out of 50 to 70. The symbol of a buffer is as follows. It's very similar to the inverter or the NOT gate, except that it does not invert. Therefore, we remove the circle. For this particular problem here, let's see how to use the buffer. So we have the AND gate, and then we follow it with a buffer, which can drive many other gates. Typically in the industry, a buffer is implemented using a series of NOT gates. If this is the input, at the output of this NOT gate, the input is flipped, and then we give another NOT gate. So the flipped input is back to its original value. This is how a buffer is implemented. The next parameter that we want to consider before choosing a logic family is propagation delay. Let's take a NOT gate. So we have the input here and the output here. Let's assume the input wave as level 0 or logic 0, logic 1, and then back to logic 0. So assume that this is the input. Now the output will be, since we have an input of 0 over here, the output is going to be a 1. Okay. Now the input is transitioning from 0 to 1. You expect to see an immediate transition in the output, but that doesn't happen. It's going to take some time because the current or the voltage has to flow through the transistor, and it's going to take some time for it to do its operation. So you're going to see a small delay, and only then you see a flip in the output. And then the input remains 1, so your output goes to 0 and remains at 0. Now you see that there is a small transition between 1 and 0 at the input. So going by the same logic, you do not see a transition in the output just yet, and it only happens after some time. This is known as propagation delay. Ideally, you would want to see the output as soon as the input changes, Therefore, it is preferred to choose a logic family which offers a lower propagation delay. Based on these two characteristics, let us look at the different logic families and how the values are typically found in these logic families. So you have the characteristics here. Let's take TTL, or the transistor-transistor logic, ECL, emitter coupled logic, and CMOS. These are the three most famous ones. Complementary metal oxide semiconductor. And let's take the parameters as fan out, propagation delay, and power dissipation. Ideally, you want the power dissipation to be low as well. For TTL, the fan out is typically 1 to 10. So TTL logic family gates can drive from 1 inputs to 10 inputs. ECL, you have 20 to 30. CMOS, you have 750. Propagation delay for TTL is 1 to 30 nanoseconds. For ECL, it is 1 to 6 nanoseconds. For CMOS, it is 1 to 200 nanoseconds. Power dissipation, that is typically in milliwatts. For TTL, you have 10 milliwatts. For ECL, you have 50 milliwatts. And for CMOS, you have 0.01 milliwatts, which is approximately 10 microwatt. So based on these three characteristics, you can choose TTL, ECL, or CMOS, and it totally depends upon the application as well. So if your application specifies that you want a lower propagation delay, then you would ideally choose emitter coupled logic. And if your application demands lower power dissipation, then you would choose CMOS.